Today we start with synthetic data. The first block actually showing you how to create a synthetic data. Synthetic data is nothing but we are actually using some random values to create a dummy data. Okay. So here you can see that there are 4 columns. Each column is maintained as a list, and each column will act as a series, and a collection of series together form a data frame. Okay. So the variable data is actually a collection of lists, and then we are actually converting that into one block is missing, right? One block, one block, I think I have deleted yesterday. Okay. df equal to pd dot, yeah. So then I'm creating that into a what? Pandas data frame. So this is a NumPy array and this is a Pandas data frame. Okay. And again, these columns are actually not having any null values, right? See, this column is not having null value, and this is having only one null value. Okay. So what I'm doing is I'm actually inducing some kind of null values at the second row, third row, and seventh row for the third column, and fifth row, ninth row, 14th row for the last column. Okay. So after that, you can see that there are more number of null values here, and that is particularly called as NaN. Okay, right? Now, how can I calculate this NaN? Okay, so how can I calculate this NaN? That is how to know about how many null values are there. For that, we have discussed this function at the time of pandas. df dot is null dot sum. That is a function. So on calling this, we can see that the columns 1, 2, the numerical columns 1, numerical column 2, categorical column 1, categorical column 2 is actually having the values 3, having 3, 2, 4, 3, 2, 3, 4 null values respectively. Okay. And to handle that, what we are actually doing. Okay. So we can make use of the fillNav function, and within that fillNav function, we have to mention about the column we need to put the null values. Okay. Now, what is the value to be filled? It is nothing but the mean of that particular column. Okay. And in place equal to true means it should be reflected on this df itself. Okay, it should be reflected on df itself. So if you're not doing this in place equal to true, then you have to write like df is equal to df dot fill now of. Okay. So in place equal to true means the change you are making should be reflected on the data frame. Okay. And the second column, second numerical column, we are filling with the median value. Okay. And for the categorical values, we are filling it
Sir,
with, yeah.
excuse me. Sir, അതിപ്പോ ഒന്നില് മീനും അടുത്തതില് മീഡിയനും ഇടാൻ കാരണം എന്താ?
That is a choice. We can actually try with mean as well as median.
Okay.
For numerical values, any of the average like mean or median can be used. Based on the evaluation, what we are actually doing is first mean വെച്ചിട്ട് fill ചെയ്തിട്ട് we will check for the performance. Then median വെച്ചിട്ടും എന്ത് ചെയ്യും, പെർഫോമൻസ് നോക്കും, ഏതാണോ നല്ലതായിട്ട് വരുന്നത് that we will choose. Okay. And for categorical columns, we usually use mode. The most repeating value will be filled on a particular missing values. Okay. Now, after that, again, we are trying the is null function dot sum. That will give you the idea of number of missing values. Now we have no missing values at all. Okay. Now, how to handle the how to handle the duplicate values. So for that, first we have created duplicate row in another data frame equal to pd dot concatenate of df dot ilog of 0. The first row will be multiplied, repeated 3 times. Okay. And it is concatenated. So you are getting a new data frame. Then the df, the current data frame, and the duplicate rows data frame are again concatenated together to form a new data set. See, there you can see the first row is duplicated here, right? And to avoid that, we have to use the function drop duplicates. Okay, drop duplicates in place equal to true. Okay, the file. So on executing this, you'll get the duplicate rows, and again you are cleaning the data. Okay, and the quartile. Okay,
സർ
so
ഒന്നും കൂടെ,
yeah,
ഇതില് പിന്നെ ഡ്യൂപ്ലിക്കേറ്റ് റോ എന്ന് പറയുമ്പോൾ എല്ലാ വാല്യൂസും ഒരുപോലെ വരുന്നതിനല്ലേ ഡ്യൂപ്ലിക്കേറ്റ് റോ എന്ന് പറയുന്നത്?
yes, values
എല്ലാ
ഒരേപോലെ.
കോളത്തിലും അത്
Yes,
നമ്മൾ ചെക്ക് ചെയ്തിട്ട് ഡിലീറ്റ് ചെയ്യുന്നു.
yeah, exactly. Okay, so the outlier, I will tell you about the outlier. What is your idea about outlier? When you think about outlier, what is your idea that comes in your mind?
ആ ഡാറ്റാ സെറ്റിൽ നിന്ന് ഡീവിയേറ്റ് ചെയ്ത് നിൽക്കുന്നതല്ലേ ഔട്ട്ലിയർ എന്ന് പറയുന്നത്?
Exactly. So how can I detect that? Okay. So I am giving an example for this. Okay.
സർ
See,
സർ ഒരു മിനിറ്റ്,
yeah,
നമ്മൾ എന്തിനാണ് ഈ ഡ്യൂപ്ലിക്കേറ്റഡ് റോസ് ആഡ് ചെയ്തത്?
അത് ഡ്യൂപ്ലിക്കേറ്റഡ് റോസ് ആഡ് ചെയ്തത് ശരിക്കും അങ്ങനെ ഡ്യൂപ്ലിക്കേറ്റിനെ ഉണ്ടാക്കാൻ വേണ്ടിയിട്ടാ. Our need is to remove that duplicate. Suppose if we are collecting a data, at some time the data may be duplicated, right?
യെസ് യെസ്.
അപ്പൊ ആ ഡ്യൂപ്ലിക്കേറ്റ് വരുന്നതിനെ എങ്ങനെ കളയാം?
അല്ല, അപ്പൊ പ്രിന്റ് ഡേറ്റ ഫ്രെയിം ആഫ്റ്റർ ആഡിങ് 3 ഡ്യൂപ്ലിക്കേറ്റ് റോസ് എന്നല്ലേ
അത്
വന്നേക്കുന്നത്?
അത് നമ്മൾ കാണിക്കാൻ വേണ്ടിയാ ഡ്യൂപ്ലിക്കേറ്റ് ഉണ്ട്.
ഓ ഓ ഓക്കെ ഓക്കെ ഓക്കെ.
ഓക്കെ, അപ്പൊ അങ്ങനെ ഒരു നാച്ചുറൽ ഡേറ്റ കിട്ടാൻ പാടായതുകൊണ്ട് വി ആർ സിന്തറ്റിക്കലി ക്രിയേറ്റിംഗ് സം ഡ്യൂപ്ലിക്കേറ്റ്സ് ടു ഡെമോൺസ്ട്രേറ്റ് ഹൗ ടു ഡിലീറ്റ് ദാറ്റ്.
ഓക്കെ ഓക്കെ.
Okay, okay, yeah. So yeah, I'm going to 30, 35, 38, 42, 41, 46, 50, 52, 101. Okay, these are some observations. Okay, so if you index this, it starts from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so maybe I can put one more data for the easiness. 29. So it would be like 1 and 0. Okay, right? And you're all able to draw a box plot from this, right? What is Q2? What is the value of Q2? What is value of Q2 here? Q2 എവിടെയാണ്? This is
42 ആണോ?
Q2. Yeah, this is Q2, right? And again, this is what? Q3.
Q3,
And this is
Q1.
Q1, right? അതെല്ലാവർക്കും അറിയാം അല്ലേ? Right? Now, the difference between Q1 and Q3 is actually called as IQR. What is that?
Interquartile range.
Tail reach, interquartile range. Okay. So here, what is IQR? IQR is equal to 50 minus 30. What is that? 20, right?
20.
Okay. Now, we will find out two bounds. Okay. An upper limit, an upper bound, and a lower bound. Upper bound is nothing but Q1 minus 1.5 IQR. So what is that? Q1 minus 1.5 IQR. Q1 is 30 minus 1.5 IQR. What is that?
30.
30.
30,
0.
0.
0, right? And upper bound is Q2 plus 1.5 IQR. What is that? Q2 is 50 plus
30.
30. That is
Q,
80, right?
Q2 42
Sorry,
അല്ലേ സാറേ?
no Q2, Q3. 80, right?
Q3.
Q3. So those observation which are less than lower bound and those observations which are greater than upper bound is actually
Outlier.
termed as outliers. Okay. So with that, who is actually one outlier?
101 value.
Yeah, 101 become the outlier.
ഇല്ല.
There is no value less than 0, right?
Okay, sir.
And there is one value greater than
80.
30, 80. That is 101. Okay, hope you are getting that, right?
Yes, sir.
Yeah. So this is the way to find out the outliers. Okay.
Is
So-
in 2 also a outlier because it is very much far from the mean value.
Yeah, but according to this condition, it is not an outlier.
So are we calculating outliers only based on this formula?
No, this is one method to find the outlier. One statistical method to find out the outlier.
So in order to find out the IQR, we have to actually sort the numbers in increasing order, right?
Yeah, now it is not in increasing order. One is changed, right? Yeah, 42, yeah. 42. I have written it in increasing order. Yeah, 41 and 42. Yeah. Still that won't make a change, right? Okay. So this is actually implemented here in the next block. See, here we have found the Q1 by taking the quantile function 0.25 quantile Q1 and Q3. We are finding the IQR Q3 minus Q1. Lower bound is equal to 1.5 Q1 minus 1.5 IQR and upper bound is equal to Q3 plus 1.5 IQR. Then we are filtering out the outliers. Outliers is equal to DF of numerical column 1 less than lower bound or DF of numerical column 1 greater than upper bound. So we are getting the outliers. Okay. And to remove it, we are negating that part. Okay. So we are getting.
So this is the general equation for all outliers. I mean,
Yeah, this is the most accepted way of finding the outliers. Okay. And the other one is again type conversion we are doing. See, we are converting the last column. See, even though it is a categorical value, it seems like numerical values, right? For categorical column 1, categorical column 2, it seems like numerical values. It is represented using decimal values, right? So there, to the categorical column 1 and the categorical column 2 can be, see, these are all what? Numerical values. So we can actually convert that type using the function as type. Okay. Column name dot as type the category. Then it will convert it into categorical values. See, previously it was float. Now it is float category. Okay. Right.
സർ അതെന്താണ് ഈ കാറ്റഗറി ആൻഡ് കാറ്റഗറിക്കൽ കോളം എന്ന് ഉദ്ദേശിച്ചത്?
നമ്മൾ ഇന്നലെ ടൈപ്സ് ഓഫ് സാധനങ്ങൾ പറഞ്ഞില്ലേ, മെയിൽ ആൻഡ് ഫീമെയിൽ, ബെസ്റ്റ്, ഗുഡ്, ബാഡ്, അല്ലെങ്കിൽ ഹൈ, മീഡിയം, ന്യൂമറിക്കൽ വാല്യൂസ് ആയിട്ട് റെപ്രസെന്റ് ചെയ്യാൻ പറ്റാത്തത്.
ഓക്കെ ഓക്കെ
ഓക്കെ.
ഈ
ചില സമയം
ഔട്ട്ലയേഴ്സിന്റെ സിഗ്നിഫിക്കൻസ് എന്താ?
ഔട്ട്ലെയേഴ്സിന്റെ പ്രസൻസ് കൊണ്ട് നമ്മളുടെ ഡേറ്റയിൽ ഒരുപാട് ഡീവിയേഷൻസ് ഉണ്ടാവും മാം.
Okay.
ഇപ്പൊ ആവറേജ് ഒക്കെ എടുക്കുമ്പോൾ ഇപ്പോ ഔട്ട്ലെയർ പ്രസന്റ് ആണെങ്കിൽ വാട്ട് വിൽ ഹാപ്പൻ ഇസ് അതിന്റെ ആക്ച്വൽ ആവറേജ് നമ്മൾ ഒരുപാട് ഷിഫ്റ്റ് ആയി പോകും.
Okay.
സോ എപ്പോഴും ഔട്ട്ലെയേഴ്സ് നീഡ് ടു ബി ഹാൻഡിൽഡ് കോഷ്യസ്ലി.
Okay.
സാറേ ഏത് മെഷീൻ ലേണിംഗ് അൽഗോരിതം ചെയ്യുമ്പോഴും നമ്മൾ പ്രീ പ്രോസസ്സിംഗിൽ ഈ സ്റ്റെപ്സ് ഈ ഓർഡറിൽ ഇങ്ങനെ ചെയ്തിരിക്കണം മാൻഡേറ്ററി ആണോ അതോ?
നിർബന്ധമില്ല. ദീസ് ആർ ഓൾ പോസിബിൾ പ്രീ പ്രോസസിംഗ് സ്റ്റെപ്പ്. അപ്പോൾ ഇതിന് ഏതൊക്കെ ഇപ്പോൾ ഔട്ട്ലെയർ ഇല്ലെങ്കിൽ നമുക്ക് ഔട്ട്ലെയർ ചെയ്യേണ്ട ആവശ്യമില്ല. ബട്ട് വി ഹാവ് ടു എൻഷുർ ഇറ്റ്.
ഓക്കെ ഓക്കെ
ഓക്കെ. നൗ
ഇപ്പൊ വലിയ ഡാറ്റ സെറ്റ് ആണെന്നുണ്ടെങ്കിൽ നമുക്ക് ഔട്ട്ലയേഴ്സ്
ഉണ്ടാവാൻ സാധ്യതയുണ്ട്. അപ്പൊ നമ്മളത് ചെയ്യുന്നത് തന്നെയാണ് ബെറ്റർ.
അതെ.
സോ ദ നെക്സ്റ്റ് വൺ ഇസ് നോർമലൈസേഷൻ.
സാറേ ഒറ്റ കാര്യം ചോദിച്ചിട്ട്, നമ്മളെ കാറ്റഗറിക്കൽ കോളത്തിന്റെ നമ്മൾ പറഞ്ഞിരുന്നത് ഫീമെയിൽ മെയിൽ അങ്ങനത്തെ സാധനങ്ങളല്ലേ?
അതെ.
അപ്പൊ നമ്മുടെ ഇപ്പൊ എടുത്തിരിക്കുന്ന ഈ ഡേറ്റ സെറ്റിലെ കാറ്റഗറിക്കൽ കോളം എന്ന് പറഞ്ഞു കൊടുത്തിരിക്കുന്നത് ന്യൂമറിക്കൽ വാല്യൂസ്.
അതെ, അൾട്ടിമേറ്റ്ലി നമ്മളത് കാറ്റഗോറിക്കൽ ആണെങ്കിൽ കൂടി ഇറ്റ് ഷുഡ് ബി കൺവേർട്ടഡ് ടു ന്യൂമറിക്കൽ. ഇപ്പൊ മെയിൽ ആൻഡ് ഫീമെയിലിനെ നമ്മൾ 0, 1.
ഓക്കെ. സോ യു ഹാവ് റീപ്ലേസ്ഡ് മെയിലിന് പകരം 0 എന്നുള്ളത് കൊടുത്ത ഡേറ്റയാണ് ഇതെന്നാണ് പറഞ്ഞത്.
അതെ അതെ അതെ. അപ്പോ അതിനകത്ത് പക്ഷേ ഈ പറയുന്ന സ്റ്റാറ്റിസ്റ്റിക്കൽ മീൻ ഒന്നും വർക്ക്ഔട്ട് ആവാൻ പാടില്ല.
അതെ അതെ അതെ.
അങ്ങനെ ഇതിപ്പോ ഇങ്ങനെ കടന്നു കഴിഞ്ഞാൽ ഇഫ് വി കൺസിഡർ ഇറ്റ് ആസ് ഫ്ലോട്ട്, അതെല്ലാം അവിടെ വരും.
ഓക്കെ ഓക്കെ ഓക്കെ.
ബട്ട് കാറ്റഗോറിക്കൽ ആണെങ്കിൽ ദാറ്റ് വോണ്ട് ഹാപ്പൻ.
ഓക്കെ. അപ്പൊ നമ്മൾ അതുകൊണ്ട് പർപ്പസ്ഫുള്ളി അത് പറയാൻ
We have
വേണ്ടിട്ട്
to make it
എഴുതിയതാണ്.
as categorical.
ഓക്കെ ഓക്കെ.
Yeah.
താങ്ക് യു.
And here the min-max scaling is there. The scaling is actually nothing but we are making the entire data into a particular range. ആ ഒരു റേഞ്ചിലേക്ക് കൊണ്ടുവരാൻ വേണ്ടിയാണ് നമ്മൾ എന്ത് ഉപയോഗിക്കുന്നത്? സ്കെയിലിംഗ് ഉപയോഗിക്കുന്നത്. ഓക്കെ. So usually the scaling will happen like, see, if I want to do a scaling, okay. If I want to do it, if I want to do scaling here, the equation is each x need to be converted as x minus x minimum divided by x max minus x minimum. ഒരു മിനിറ്റ്. Sorry. X max x minus x minimum divided by yes, x minimum. Okay. So what is the maximum value here? 101. What is the minimum value here? 2. Right? So what will happen if x is x minimum itself? X minimum minus x minimum by x max minus x minimum, right? So the minimum value will be changed to 0 always. Okay. And what will happen if x is x max?
1.
X max minus x minimum divided by x max minus x minimum, right? It become 1. So the minimum value will be converted to 0 and the maximum value will be converted to what? 1. All other values will be converted in between
0
what?
0
and
to
1.
1.
0
0
to
and
1.
1.
See, if like we can consider this 52, what will be happening? 52 minus 101 divided by, sorry, 52 minus 2 divided by 101 minus 2. So it will be like what?
Sir, 101 എടുക്കുവോ അത് ഔട്ട്ലിയർ ആയിട്ട് പോയതിനു ശേഷം
അല്ല ഇത് പോയി ഇപ്പൊ അതെല്ലാം ഉണ്ടെന്ന് വിചാരിച്ചാൽ 50 by 99, right? Something like 4.999 something, right? അപ്പൊ ഒരു ചെറിയ റേഞ്ചിലേക്ക് കൊണ്ടുവരാനാണ് ടു മേക്ക് ഇറ്റ് ബിറ്റ്വീൻ 1 and 0 ആണ് നമ്മൾ എന്ത് ഉപയോഗിക്കുന്നത്? സ്കെയിലിംഗ് എന്ന് പറയുന്ന പ്രോസസ്സ് ഉപയോഗിക്കുന്നത്. സോ ഹിയർ ഇവിടെ നമുക്ക് കാണാം ദ ന്യൂമറിക്കൽ കോളംസ് ആർ 12, 10, 12, 9, 55, 62 എന്നൊക്കെ പറഞ്ഞിട്ടുള്ള വാല്യൂസ് ആയിരുന്നു. ബട്ട് ആഫ്റ്റർ ദ സ്കെയിലിംഗ് പ്രോസസ് see it become values between 0 to 1. Clear അല്ലേ? Is that clear?
സാറേ
Sir,
അവിടെ ആ
ഹലോ സർ
101 ഒഴിവാക്കിയില്ല.
ഏതാ?
101 എടുക്കുന്നുണ്ട്.
ഇവിടെ
ഔട്ട്ലേ
ഞാനൊരു എക്സാമ്പിളിന് വേണ്ടിയിട്ട് ഈ ഡേറ്റ തന്നെ എടുത്തേ ഉള്ളൂ.
ഓക്കെ സാർ.
And if you
ഹലോ
want to
സാറേ ഹലോ
yes ദീപക
സർ
പറഞ്ഞോളൂ.
ഈ സ്കെയിലിംഗ് എന്തിനാ ഉപയോഗിക്കുന്നത് ശരിക്കും നമ്മൾ?
സ്കെയിലിംഗ് എന്തിനാ ഉപയോഗിക്കുന്നതെന്ന് ചോദിച്ചു കഴിഞ്ഞാല് യൂഷ്വലി നമുക്കിപ്പോ ഒരു സാലറി എന്ന് പറയുന്ന ഒരു കോളം ഉണ്ടെന്ന് വിചാരിക്കും. സപ്പോസ് വി ആർ ഹാവിംഗ് എ കോളം ലൈക്ക് സാലറി. ഓക്കെ, സോ നമ്മൾ ചെയ്യുന്ന ഓൾമോസ്റ്റ് ഓൾ കമ്പ്യൂട്ടേഷൻസ് വിൽ ബി ഹാപ്പനിങ് ഓൺ എ ബിഗ് വാല്യൂ, റൈറ്റ്? സാലറി എല്ലാവർക്കും ഒരു 10,000 or 1 lakh റേഞ്ചിലാണെങ്കിൽ if the salary is in the range between 10,000s and lakhs, okay, the comparisons is everything happening on this big range of values. Okay, but if there any relevance in keeping the big values, because minimum salary like 10,000 salary ഉള്ള ആളെ 0 എന്നും 1 lakh salary ഉള്ള ആളെ 1 എന്നും എടുത്തു കഴിഞ്ഞാൽ
1 lakh ഉള്ള ആളെ ഒരു 1 എന്ന് എടുക്കും.
but we can still compare that quantities, right?
Oh, I see.
So that will reduce the computational time. Okay, and we will
Sir.
get the same effect of that of the actual data.
Okay. Actual data. See, sir.
Yeah.
Thank you, sir.
Anything, Gaurav?
Sir, like question was why we are doing this scaling. Is that
Scaling.
correct?
Yes.
Why
yes,
we
yes.
are doing this scaling?
Yeah, why we need to go for the scaling?
Or sir, another like just to understand this 101, we should remove as outlier or we should keep as outlier and then do the scaling. Why it is something?
Usually we will do like we will first remove 101 as an outlier.
Okay.
Then we will go for the scaling.
But since we have already removed this height like outliers,
Yeah.
scaling, how does it help? Like let's say I have removed 101, so now my most of the scale is on same ground, right? Same values almost.
But sometimes
Okay.
if you simply consider the salary,
Okay,
as a column, the highest salary will be, the minimum salary will be 10,000, 20,000, okay,
yeah,
30,000 and so on, and someone is having 55,000 and the maximum salary is 10,000, okay, sorry, 1 lakh.
okay.
So comparing these salaries for a particular decision making is same as that of if you map this to 0, okay, this to 1 and this to 5.5, right? Sorry,
0.55.
0.55.
Yeah.
The same comparison effect will be retained. But we can actually reduce the computation.
Okay. But sir,
Okay.
this sorry, question is
Ah.
we will do if outlier first, right? This 1 lakh might be removed as an outlier. That's my
No, but
should we
if you consider this data, 10,000, 20,000, 30,000 and all, this 1 lakh will not go as an outlier.
But in some cases, like not like in this 101 is getting removed as outlier, right? So
Yeah.
then your max will be only 52 in that case, correct?
Yes, yes, yes.
So that's what like so should we remove outlier or because we should do scaling first and then outlier? Something that's my confusion, like
See,
sequence. I am
even
confused
though
more.
if you do scaling here,
Okay.
then if you calculate outlier, that will also remove that 10.1.
Okay. Okay.
Yeah. The
Okay.
scaling will not affect the outlier detection.
Okay.
Because if you reduce it into a smaller range, say maybe I'm dividing everything by 10, 0.2 to 0.9 to 3.0, 3.5, 3.8, 4.1, like that, right?
Okay.
Then what will be your interquartile range?
Like quarter range might be like just point, it will be just fractions, right?
It become 2.
2.
Right?
Yes.
Again, if you calculate outliers, this 10.1 will go as an outlier.
Yeah, but with the scaling, because it will now become 0 and 1 only, right? So
Yeah, still
okay.
if
Okay.
you simply do scaling at this point also,
Okay.
it
Okay,
will
sir.
go as an outlier.
Okay. Okay.
Did you get that?
Yeah. Basically, we can do like my question was when we are doing processing, should we first remove outlier and then do scaling, or we can do
Yeah,
vice versa both?
we have to do the outlier detection first, then
Okay, and
remove
then
the
scale.
yeah.
Okay.
Yeah. Okay, and there's something called another scaling which is called as standard scalar. That what it will do is it will do a normalization. That is, it will first, if suppose you are having a set of observation x1, x2, etc. up to xn, it will first find the mean of it. Okay, how we will find it? Sigma xi by n, right? Then also it will find out the standard deviation. Okay, then each xi will be calculated as change to xi minus x mean divided by sigma. That is what we are calling as standardization. Standard scalar. Okay, standard scaling. And it is a kind of normalization too. Okay. That's also a choice. Then the transformations are there. The transformations are something like if a data is not maintaining a particular distribution. As I said, for every data, we are expecting that data need to be in normal distribution, right? So if some data is not following normal distribution, we can use this kind of transformations. Okay. So there is something called quantile transformation. There is something called power transformation. These are all small equations that makes data into another form. Okay. So here I am demonstrating the quantile transformation and power transformation. Okay. So here this is one numerical column. After applying the quantile transformation, the histogram is actually getting changed, right? Somehow the skewed kind of thing will be following a kind of what? Normal. Here also you can see that it is actually the power transformation is also converting the data into a normal form. Okay. So this is also a pre-processing step, but this is an optional thing. I never see this transformations on every pre-processing pipeline. If you want to make it into a normal or uniform distribution, you can make it as
സാർ ഈ ക്വാണ്ടൈൻ ട്രാൻസ്ഫോർമേഷൻ അത് എങ്ങനെ ചെയ്യുന്നതെന്നാ പറഞ്ഞത്?
in the theory, it's a bit complicated thing. That is why I'm not explaining. Okay.
Okay.
Yeah. It's actually a kind of equation we need to follow. Scaling there is an equation.
ഞാൻ എവിടെ ഈ ക്വാണ്ടൈൻസ് കേട്ടിട്ടുണ്ട്, അത് എനിക്കത്.
Yeah.
സാർ ഒരു ഡൗട്ട് ചോദിച്ചോട്ടെ. നേരെ മിനിമാക്സ് സ്കെയിലിംഗ് പറഞ്ഞു, പിന്നെ സ്റ്റാൻഡേർഡ് സ്കെയിലിംഗ് പറഞ്ഞു. രണ്ടും 0യുടെയും 1ന്റെ ഇടയ്ക്കൊക്കെ കൊണ്ടുവരുവാണോ ഡാറ്റ?
അല്ല, the standard scaler will make the mean to 0. The entire data mean 0 ആക്കി നോർമലൈസ് ചെയ്യുക ചെയ്യുന്നത്.
ഓക്കെ. അപ്പൊ ഏതെങ്കിലും ഒരെണ്ണം ഉപയോഗിച്ചാൽ മതി നമ്മള്, ഡിപ്പെൻഡ് ഓൺ ദി
യൂസ് കേസ്.
ഓക്കെ.
Again,
നമ്മള് ഇപ്പോ നമ്മുടെ ഡാറ്റാ സെറ്റിൽ നമ്മൾ ഡാറ്റ നോക്കുമ്പോഴേ ഇപ്പൊ പോസിറ്റീവ്ലി സ്ക്യൂഡ് അല്ലെങ്കിൽ നെഗറ്റീവ്ലി സ്ക്യൂഡ് കുറച്ചെങ്കിലും കാണുകയാണെങ്കിൽ നിർബന്ധമായിട്ടും അതിനെ ഒരു നോർമൽ ഡിസ്ട്രിബ്യൂഷനിലേക്ക് കൊണ്ടുവരണം എന്നുണ്ടോ?
നോർമലി ഡിസ്ട്രിബ്യൂഷൻ ആക്കിയാൽ ഇറ്റ് ഈസ് ഗുഡ്.
ഓക്കെ.
ഒരു ഡൗട്ട് ചോദിച്ചോട്ടെ.
ഇതിന്റെ
എനിക്ക് ആകെ കൺഫ്യൂഷൻ ആയെന്ന് വെച്ചാൽ നമ്മളുണ്ടല്ലോ ഈ ഡാറ്റ നമ്മൾ ഈ തിയറി പഠിക്കുമ്പോഴേ നമ്മൾ ഈ സ്മൂത്തിങ് ടെക്നിക്സ്, അപ്പൊ സ്മൂത്തിങ് ക്ലീനിങ് ഒക്കെ ഏകദേശം ഒന്ന് തന്നെയാണോ? അപ്പോ
സ്മൂത്ത് ക്ലീനിങ് ഇൻവോൾവ്സ് എ ലോട്ട് ഓഫ് സ്റ്റെപ്സ് മിസ്സേ.
അല്ല, നമ്മളുണ്ടല്ലോ ഇപ്പൊ ഇതിനകത്ത് നമ്മളിപ്പോ ബിന്നിങ് എന്ന് പറഞ്ഞിട്ടുണ്ടല്ലോ,
അത് കൈൻഡ് ഓഫ് സ്മൂത്തനിങ് ആണ്.
ഓക്കെ. അപ്പൊ സ്മൂത്തനിങ് എന്ന് പറഞ്ഞാൽ ശരിക്കും ക്ലീൻ എന്ന് വെച്ചാൽ നമ്മൾ ഈ തിയറി മാത്രം കണ്ടിട്ടുള്ള പ്രശ്നമാണെന്ന് തോന്നുന്നു. എനിക്ക് അപ്പൊ ശരിക്കും ക്ലീനിങ് എന്ന് പറയുന്നത് ഇതൊക്കെ സെയിം തന്നെയാണോ?
ക്ലീനിങ് എന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇപ്പോ ഇംപ്യൂരിറ്റീസിനെ കളയുക. ദാറ്റ് ഇസ് വാട്ട് യു ആർ മീനിങ്, വാട്ട് വി ആർ ഇന്റെൻഡിങ് ഫ്രം. അല്ല, ഇംപ്യൂരിറ്റീസിനെ കളയുക എന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇറ്റ് ഇസ് നോട്ട് ഓൺലി ഔട്ട്ലയേഴ്സ്. Removing impurities intended in cleaning. That would be missing values ആവാം, outliers ആവാം, duplicates ആവാം. These are all impurities. So removing all these things actually called as what? Data cleaning.
അപ്പൊ ഈ നമ്മള് ശരിക്കും ഇപ്പൊ ഈ മിൻമാക്സ് ആണെങ്കിലും നമ്മൾ പറഞ്ഞ ഈ സെറ്റ് സ്കോറും എല്ലാം ചെയ്യുന്നത് ഏതെങ്കിലും ഒരു വാല്യൂയിലേക്ക് നമുക്ക് പ്രോസസ് ചെയ്യാൻ വേണ്ടിയിട്ടുള്ള എളുപ്പത്തിന് വേണ്ടി ചെയ്യുന്നു എന്നാണോ എന്റെ മീനിങ്?
അതെ. യെസ്. ആൻഡ് ഓൾസോ ഈ മെഷീൻ ലേണിംഗിന്റെ തിയറീസ് നമ്മൾ സ്റ്റാർട്ട് ചെയ്യുമ്പോൾ വി ഹാവ് ടു ടേക്ക് സം അസംഷൻസ് ഓൺ ദ ഡേറ്റ. every feature should be in normal distribution. That is one rule. And അതുപോലെ every classes, if you have a label column, that label column should follow a uniform distribution. The correlation between two columns should be minimum. അങ്ങനെ കുറെ കാര്യങ്ങൾ നമുക്ക് എൻഷുർ ചെയ്യാനുണ്ട്. അപ്പൊ ഇതിലേക്ക് എത്തിക്കാൻ വേണ്ടിയാണ് വി ആർ ആക്ച്വലി ഡൂയിങ് ദിസ് പ്രീ പ്രോസസിംഗ്. എങ്കിലേ ഈ അൽഗോരിതംസ് പ്രോപ്പർലി വർക്ക് ചെയ്യുള്ളൂ.
കാര്യങ്ങൾ സാർ പിന്നീട് പറയോ?
ഏതാ?
ഇപ്പൊ നേരത്തെ സാർ പറഞ്ഞില്ല, അതായത് ഇങ്ങനെ കുറച്ച് കാര്യങ്ങൾ എൻഷുർ
Yes.
ചെയ്യേണ്ടതുണ്ട്.
That is what we are discussing in inductive bias.
Okay.
Yeah, we are actually going to discuss while starting with the algorithms. Okay. Yeah. So the discretization and binning is again, see, suppose we are having a continuous value, any value between 0 to 100. Okay. But we have to make it as categorical. അപ്പൊ നമുക്ക് എന്ത് ചെയ്യാം? നമ്മൾ ടാലി ഒക്കെ ചെയ്യില്ലേ, അതുപോലെ I'm repeating. Suppose you are having a value between 0 to 100. Any continuous value can be there. Maybe the percentage marks or the marks or any other scale value, something like that. Okay. But for the easiness of making decisions, I want to make it into slabs. 0 to 10, 10 to 20, 20 to 30. That is how we are doing the tally marking, right?
Yes, grading for like.
Yeah, so that is what we are actually calling as discretization. Okay, so a continuous value need to be converted into a discrete value. And binning is again, if you have a long range of value, make it into different buckets. Okay. Both of the things are actually implying the same thing. Okay. So for that also, I'm just creating a new data here. See, we have income, years of experience, spend per visit, visit per month, customer values, right? Now what I'm doing is, see, I'm doing a binning. Okay. So for that, I'm taking the maximum value in the income, minimum value in the income, and instead of keeping the income like this, I want to make it as low, medium, high, very high. Okay. So what I will do, I'm converting df.due income bin equal with. Okay. Now use the function cut, and we have to cut the income. Okay. Equally cut the entire data in the income column, and bins is equal to, we have to take the number of bins. How many bins are there? 1, 2, 3, 4. 4 bins are there. So the entire range will be equally divided into 4 bins, and the bin labels are also there. Then include a lowest value also true. Okay. Right? And see, this is actually called as quartile cuts. Okay, Q cut. Q cut is actually based on the frequency of each thing. We need to divide the entire slab into varying slabs, but frequency must be equal there. That is Q cut. Okay, you can see the results over here. See, so in simple cut, the entire thing, that is the entire range. Here the maximum value will be, you can actually print this to print minimum income. Okay. So we are printing the minimum income, that is 20501, maximum income 1,49,905. The entire range is divided into 4 bins. Okay. So the bin ranges are from 205012 to 36869. Okay. So likewise, we are dividing the entire range into equal bins. Okay. And for Q cut, what we will do is, to make the frequency of each bin equal, we will vary the intervals. That is actually the Q cut and cut. Okay. So after this, we can convert our data, income data, into a particular, this is a numerical value, right? Now we have converted it into a categorical one, a distinct one. Okay. So this is also showing the another example. So in discretization, mostly we are taking the intervals. Okay. From this range to this range, this range to this range. So this will be considered in what? Discretization. So anyway, it is converting the entire values into different bins. Okay. Yeah. Now, polynomial features and interaction features. See, this is actually we tried to create some data. I can show you this. Yeah. The theories of all these things are actually there in the slides, feature extraction. Okay. These things are actually there. Okay. Yeah. The polynomial and interaction features. So what we are actually doing is, see, suppose you are having one variable x and one output variable y. Okay. So if you try to fit a line for this particular distribution of data, it won't work, right? Okay, it won't work. So what we are actually doing is, we are actually need to create a curve like this. Okay, a curve like this. So instead of the data that x and y, sorry, x and y, we convert that to x square y. Then we will try to again fit a linear thing. So this will be considered as x1, this will be considered as x2. So y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. This is also a linear model, but here x2 is what? It's actually the square of x1, right? Okay, square of x1, square of x. So ultimately, we are able to tackle the non-linearity in the data. Okay, so it's nothing but we are introducing new features by creating the polynomials of existing one. Suppose you are having x1 and x2 as two features. We can create the polynomials features as x1 square, x2 square, also x1 and x2, right? The three new features can also be created for tackling the nonlinear relationship. Okay, so that is what we are actually calling as polynomial and interaction features. Okay.
സാർ ഒരു ഡൗട്ട് കേട്ടോ, നേരത്തെ ക്വസ്റ്റ്യൻ ആണ്. നമ്മൾ നേരത്തെ ഡിസ്ക്രിറ്റൈസേഷൻ എന്ന് പറഞ്ഞില്ലേ? അപ്പൊ അവിടെ ഇപ്പൊ നമ്മൾ 4 കാറ്റഗറി ആയിട്ട് നമ്മുടെ മൊത്തം വാല്യൂസിനെ ഡിവൈഡ് ചെയ്ത് 4 ബിന്നിലേക്ക് ഇടുമ്പോ അതിന്റെ റേഞ്ച്, അതായത് ഇപ്പൊ ലോ എന്ന് പറയുന്നത് അതിന്റെ റേഞ്ച് എങ്ങനെയായിരിക്കും?
അത് രണ്ട് കട്ടില് the entire minimum and maximum is divided into 4 equal slabs.
4 equal.
അങ്ങനെ. And Q കട്ടില് ഈ 4 എണ്ണത്തിലും ഈക്വൽ നമ്പർ ഓഫ് ഫ്രീക്വൻസി വരുന്ന രീതിയിൽ we will separately split each slab. അത് ഈക്വൽ സ്ലാബ്സ് ആയിരിക്കില്ല.
മനസ്സിലായി. അപ്പൊ നമ്മളിപ്പോ ചിലപ്പോ എന്ന് വെച്ചാൽ ഒരു പെർട്ടിക്കുലർ വാല്യൂ അതിന്റെ അപ്പുറത്ത് ഒരു +2 -2 രണ്ട് റേഞ്ചിലേക്കൊക്കെ പോവില്ലേ?
പോവാം.
അപ്പൊ അതിനെ നമുക്ക് ഡീൽ ചെയ്യാനായിട്ട് എന്താ ചെയ്യാ? ഇപ്പൊ നമ്മള് അതായത് ലോ എന്ന് പറയുമ്പോ ഒരു 5026 എന്ന് പറയുന്നത്
കൂടുതൽ ബിന്നുകൾ ഉണ്ടാക്കാന്നല്ലേ പറ്റുള്ളൂ, അല്ലെങ്കിൽ പിന്നെ ഓവർലാപ്പിംഗ് ബിൻസ് എടുക്കണം. ആ കേസുകളിലാണ് മിസ്സേ നമ്മൾ ഇതിൽ നിന്നും മാറി, ഈ ഡിസ്ക്രീറ്റ് ഒബ്സർവേഷൻസിൽ നിന്നും മാറി വി ആർ ടേക്കിംഗ് ഫസി.
അത് വേറെ ഒരു മേഖലയാണ് അല്ലേ?
യെസ്. അതായത് ഇഫ് എ പർട്ടിക്കുലർ തിങ് is having a membership in both the things, both sets. അപ്പൊ പക്ഷെ ഒന്നിലുള്ള ഡിഗ്രി മെമ്പർഷിപ്പ് ആയിരിക്കില്ല അടുത്തതിൽ വരിക, ഒന്നിലത് കൂടുതലായിരിക്കും അടുത്തതിൽ അത് കുറവായിരിക്കും. അവിടെ അങ്ങനത്തെ എക്സ്പ്രഷൻസിന് വേണ്ടിയിട്ടാണ് നമ്മൾ ഫസീനസ് ഉപയോഗിക്കുക. ഓക്കെ.
ഓക്കെ സർ.
Yeah, so that is what we are creating here in interaction features. Okay, this is also a not much used thing, but still we can make use of it. Okay. Now, this is a very important one, the encoding technique. The encoding techniques, we usually do 3 different kind of encodings. The first one is label encoding. Okay. In label encoding, what we are actually doing is, see, Here we have red, blue, green, blue, red, green, blue, red, right? And these are all categorical values. So whenever there is a categorical value, we have to convert it into numerical one, right? And we are using the label encoder, okay? And we are encoding the size, small, medium, large. This as an encoder thing. So we are introducing a new row, df.encode of size encoded, label encoder.fit of df of encode of size. Okay, so we will introduce a new column where the small will be encoded to 2, the medium will be encoded to 1, and the large will be encoded to 0. And how this is actually happening? Based on the alphabetical order. In large, medium, small, which is alphabetically small, large. So it will be mapped to 0. Medium will be 1 and small will be 2. Right? This is what we are calling as label encoding. Okay. And in one hot encoding, see, what we are actually doing is, suppose we have a quantity like this in a particular column, X, we have S, 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 no, no, yes, no. Okay. So how many distinct features are there? How many distinct values are there next?
2.
2. Right? So we transform this into XY and XL. Then since it is Y, we put 1 on here, 0 here. 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. Are you getting it? If there are 3 values like this, red, blue, green, red, green, blue, like this, how many distinct values are there in this particular column? 3, right? So we are converting color into color blue, color green, color red. So the red will be represented as 0, 0, 1. The blue will be represented as 1, 0, 0. Green will be represented as 0, 1, 0. This is what we are calling as one hot encoding. Hope you are getting this, right?
അപ്പൊ പുതിയ കോളം ക്രിയേറ്റ് ചെയ്യണം നമ്മുടെ എക്സിസ്റ്റിംഗ് കോളം വെച്ച് നോക്കിയാൽ
either we can create new column അല്ലെങ്കിൽ റീപ്ലേസും ചെയ്യാം. We can convert this into ഇത് ഡിലീറ്റ് ഇത് റിമൂവ് ചെയ്തിട്ട് ഇത് മാത്രം വെക്കാം. Okay. So this is what we are calling as one hot encoding. Okay. So അതിന്റെ theories ഇതിനകത്തുണ്ട്. If you look into the encoding techniques, the green, red, black, orange will be converted to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. ഇങ്ങനെ മാറും. Okay. And label encoding, every value will be mapped into a particular numerical values. That is label encoding. And ordinal encoding, the order will be kept. Okay, we can actually take the order small enough to excel. Yeah.
ഒരു കാര്യം ചോദിച്ചോട്ടെ, ഈ എന്താണ് വൺ ഹോട്ട് എൻകോഡിംഗ് എന്ന് പറയുന്നതിൽ നമ്മൾ ഒരു കളറിന് അപ്പം 4 കോളംസ് വരില്ലേ റെപ്രസെന്റേഷൻ
വരും.
അപ്പൊ അതിന് നമുക്കൊരിക്കലും സെപ്പറേറ്റ് ചെയ്യാൻ പറ്റില്ലല്ലോ. അല്ല, അത് സെപ്പറേറ്റ് ചെയ്യാൻ പറ്റില്ലല്ലോ.
അല്ല, 4 കോളം കൂടെ വെച്ചിട്ടാണ് നമ്മൾ അതിനെ ഐഡന്റിഫൈ ചെയ്യുക.
അപ്പോൾ അതേ സാധനം ശരിക്കും വേറൊരു നമ്പർ സ്കീം പോലെ ഇപ്പോൾ 1 2 3 4 5 കൊടുക്കുന്നതും ഈ ഓരോ കളർ ഇപ്പോൾ 1 2 3 3 കളേഴ്സ് ആണല്ലോ ഉള്ളത്. അത് അങ്ങനെ കൊടുക്കുന്നതും ഇങ്ങനെ കൊടുക്കുന്നതും തമ്മിൽ ശരിക്കും കോംപ്ലിക്കേഷൻ ഉണ്ടാവുമല്ലേ ചെയ്യുക? അല്ല അതിൽ വേറെ
കോംപ്ലിക്കേഷൻ ഉണ്ട്, ബട്ട് there are some needs.
ഓക്കെ വേറെ എന്തെങ്കിലും ഇത് വരാം.
നമുക്ക് ന്യൂറൽ നെറ്റ്വർക്സിലൊക്കെ വരുമ്പോൾ അതിന്റെ ആവശ്യം തന്നെ ഉണ്ട്. വൺ ഹോട്ട് എൻകോഡിംഗിൽ റെപ്രസെന്റ് ചെയ്താലേ ചില കാര്യങ്ങൾ നടക്കുള്ളൂ എന്നുണ്ട്.
ശരി.
Okay. So next part is very important that I am going to discuss, we need at least one hour to discuss that. Okay, that is why I said we are going to discuss more important things today. Okay. See, dimensionality reduction. Dimensionality reduction is actually one of the important topic in machine learning. Every time when you attend any workshop or any interviews, you can actually expect questions from this particular topic. Okay. So dimensionality reduction. Dimensionality reduction of a machine learning or dimensionality reduction concerned in machine learning actually deal with reducing the dimensions of data. Okay. Reducing the dimensions of data. So as I said, if we have n columns, x1, x2, x3, etc. up to xn, okay, then we have observation 1, observation 2, observation 3, etc. up to observation m. Okay. So what is the matrix we have? What is the dimension of this matrix?
M by N matrix.
M by N. Okay. So dimensionality reduction particularly means reducing this m by n into some m dash n dash, where m dash is less than m and n dash is less than n. Okay. And this m dash to m, reducing this, ഇതിനെ നമ്മൾ പറയാ numerosity എന്നാണ്. Numerosity and numerosity reduction. Feature reduction. Okay, right?
Yes.
And ഇത് ടുഗദർ ആയിട്ടാണ് നമ്മൾ ഇതിനെ എന്ത് വിളിക്കുക? ഡയമെൻഷനാലിറ്റി റിഡക്ഷൻ എന്ന് പറയുന്നത്. Okay. But
Sir, numerosity reduction means number of records, right?
number of records, the number of observations we can reduce.
Yeah, okay.
And the other one
feature
is number of features we can reduce.
columns, yeah, basically parameters.
But we usually don't reduce the number of rows because we need as much
More
data for
Yes.
machine learning. But this features are actually one important thing need to be reduced. Okay. Because unwanted features will point to incorrect results. Also, it will also increase the computational cost. Okay. And there is a term called curse of dimensionality, because we may think like as the number of features increases, the clarity of data also increase and it will give more good results, right? But the thing is different. As the number of features increases, after a particular threshold, it will adversely affect the performance of the model. Okay. Right? So usually the dimensionality reduction implies the numerosity reduction and feature reduction. But most of the time, we only focus on what? Feature reduction only. So that is why people are actually saying new dimensionality reduction is dealing with reducing the number of features. So dimensionality simply refers to the number of features. See, okay. When the number of features in very large relatively to the number of observations in your data, certain algorithms struggle to train effective models. This is what we are calling as curse of dimensionality. So from this point, this is very importantly, you have to keep in mind, this dimensionality reduction can be done in two different ways. The first thing is what? Feature selection. Okay. Dimensionality reduction can be done in two different ways. The first thing is called as
Feature selection.
Feature selection. The next one is actually called as feature extraction. So most of the time people get confused with this. What is this feature selection and feature reduction, feature extraction? Okay. So I will tell you one thing. The feature selection. Feature selection. Okay. In feature selection, suppose we have a feature set like F1, F2, etc. up to Fn. Okay. there are n features, we convert this f into f dash, where f1, f2, fm dash, okay? And we can always say that f dash is a subset of what?
F.
F. അതായത് നമുക്കുള്ള സെറ്റിൽ നിന്നും suppose we have a set, feature set like age, height, mark, gender, weight. Okay. From this, I am concluding that for my problem, the only things are is height and weight. So this is f and this is f dash, right? This is what we are calling as, feature selection. Is it clear?
Yes.
Everyone? Yes. The next one is a bit confusing. Feature extraction. Okay. So here I could say I have f, f1, f2, f3, etc. up to fn. Okay. And f dash is there. f1 dash, f2 dash, etc. up to fm dash. Okay. But here f dash is not a subset of f1. It is a transformation of f. What does that mean? It is a transformation of f. That is, we are creating a new set of f1 dash, f2 dash, fm dash, etc. from the existing f1, f2, f etc. to fn. Clear?
അതായത് എണ്ണം സെയിം ആയിരിക്കും, ഫീച്ചറിൽ വ്യത്യാസം
ഇല്ല,
ഉണ്ടാവും.
എണ്ണം ചെറുതല്ല, എണ്ണം സെയിം അല്ല. m will be always less than n ആയിരിക്കും.
ട്രാൻസ്ഫോർമേഷൻസ് അപ്ലൈ ചെയ്യുന്നുണ്ടെന്ന് ലൈഫിലെ.
That is, this f1 dash, f2 dash, etc. up to fm dash is not at all a subset of f. Not at all a subset of f. This f1 dash, f2 dash, etc. up to fm dash is actually created from f1, f2, f3, etc. up to fn by applying a transformation. Still, നിങ്ങൾക്ക് ഒരു ക്ലാരിറ്റി കിട്ടിയിട്ടുണ്ടാവില്ല. Okay. Yeah.
അതായത് ഇപ്പൊ നമ്മളുടെ കയ്യിൽ വരുന്ന ഡാറ്റയിൽ നിന്ന് ആദ്യം തന്നെ നമ്മൾ ഒരു ലാർജ് സെറ്റ് ഓഫ് ഫീച്ചേഴ്സിനെ സെലക്ട് ചെയ്തിട്ട് അല്ലെങ്കിൽ കണ്ടുപിടിച്ചിട്ട് അതിന്റെ അകത്തുനിന്ന് ട്രാൻസ്ഫോർമേഷൻ ചെയ്ത് എടുക്കുന്ന ഒരു സെറ്റ് ഓഫ് ഫീച്ചേഴ്സ് എന്നാണോ ഈ എഫ് ഡാഷ് എന്ന് ഉദ്ദേശിക്കണേ?
നമ്മുടെ കയ്യിൽ ഓൾറെഡി ഒരു സെറ്റ് ഓഫ് ഫീച്ചേഴ്സ് ഉണ്ട്.
അതെല്ലാം പലതരത്തിൽ ട്രാൻസ്ഫോം ചെയ്തെടുക്കണം.
അതെല്ലാം ട്രാൻസ്ഫോം ചെയ്തെടുക്കുന്ന ഒരു ന്യൂ സെറ്റ് ആണ് നമ്മളുടെ എന്തോ എല്ലാം സെലക്ട് ചെയ്യില്ല. അല്ല, അതായത് ഇതിനകത്തുള്ളതെല്ലാം ഇതിനകത്ത് വരണമെന്ന് നിർബന്ധമില്ല. ഓക്കെ, അതിനൊരു സിമ്പിൾ അനലോജി ഞാൻ പറഞ്ഞുതരാം. See, I am having a toy like this. Okay, I am having a toy like this. So the toy is actually described using its width, height, width, length, and height. Okay. So we have three features: width, length, and height. And we need to predict the cost of the toy. Okay. We need to predict the cost of the toy. And what you actually know, as length increases, width increases, height increases, what will happen? The cost will increase, but I don't know in what way the cost is actually increasing. So there is an uncertainty, right? And still there is a hidden pattern, because impact of LWH will impact on what? Cost. Okay. So here we have three features and one target, right? Can we do the same thing with less number of features?
Calculate the area and probably.
Calculating the area, that will...
Or volume, basically.
See, instead, see. Okay. If I consider this DB, that is the base diagonal, what is that? DB equal to root of L square
plus
W square, right?
Yes.
Right? So if L increases, W increases, DB will also increase, right?
yes.
Okay. So we got the impact of both L and W in DB. Right? Now consider this particular diagonal. What is that? DL, D lateral. DL is equal to
Square root
root
of L
of
square plus H square.
H square plus DB square. Right? And DL is equal to root of H square plus L square plus W square, right?
Yes.
So the data DL cost is enough for this problem, right? Right? So the feature, the new feature is what? The new feature is
derived from
DL.
all the three.
Yeah, DL, which is equal to root of L square plus H square plus W square, is actually a transformation we applied on the feature set L, W, H. Is that clear?
Yes.
Right? So the new set of features will be some transformations of what? The existing features.
Basically.
Is that clear?
Yes.
Hope you got it, right?
Yes, sir.
Yes. So this is what we are calling as feature extraction. Okay. From the existing set of data or from the existing set of features, we need to extract a set of new features by applying some kind of transformation.
സാർ ആക്ച്വലി ഇവിടെ നടക്കുന്നത് നമ്മൾ ഇപ്പൊ ഇതിനെ ഹിഡൻ പാറ്റേൺ ഫൈൻഡ് ഔട്ട് ചെയ്യുന്ന പോലെ എന്തോ സംഭവങ്ങളല്ലേ, അത് റിലേഷൻഷിപ്പ് കണ്ടുപിടിക്കുക തന്നെയല്ലേ?
യെസ്, എക്സാക്ട്ലി. അതുകൊണ്ടാണ് നമ്മൾ ഇതിനെ ഒരു അൺസൂപ്പർവൈസ്ഡ് ലേണിംഗ് കാറ്റഗറിയിൽ പെടുത്തുന്നത്. നമ്മൾ അത് പറയുമ്പോൾ പറയാം.
ഓക്കെ സാർ.
യാ. സോ
ഇവിടെ മെട്രിക്സിന്റെ ആവശ്യം. ഹലോ
ഹലോ
You can actually calculate DL if you know these things. Why you need a matrix there? You can just write the equation, right?
Yeah, but if we have in this particular scenario, this is possible. This for this particular problem, this is possible, right? But if you have a general data like this, a data like this, with m number of rows and n number of columns, can we apply the same thing here? ഇപ്പൊ നമ്മൾ പറഞ്ഞ പോലെ ഒരു ലോജിക്ക് നമുക്ക് ഇതിൽ നിന്ന് ഏത് ഡേറ്റയ്ക്കും വേണ്ടി ഡിറൈവ് ചെയ്തെടുക്കാൻ പറ്റുമോ?
ഡിറ്റർമിനന്റോ അങ്ങനെ എന്തെങ്കിലും മതിയാവോ?
Still it won't keep the number of data, right? So അവിടെയാണ് yeah.
Like if you're not able to find something out of this, how can we extract the feature?
Yeah, that is what is happening with the matrix decomposition.
സാർ നമ്മൾ സാധാരണ അതിൽ ട്രാൻസ്ഫോർമേഷൻ ഒക്കെ മെട്രിക്സ് ആയിട്ടല്ലേ റെപ്രസെന്റ് ചെയ്യുക, സ്കെയിലിംഗ് ആണെങ്കിലും ഒക്കെ. അതുകൊണ്ടാണോ ഇങ്ങനെ റെപ്രസെന്റ് ചെയ്തത്?
അല്ല, this is our data and this data can be reduced into another matrix. നമ്മളുടെ കണ്ടീഷൻ എന്താ? The number of rows should be same, right?
Okay.
Number of columns should be reduced, n dash.
Okay.
So how can I do this? And for doing this, we have a specific linear algebraic mathematical concept called matrix decomposition. Okay, so there are a lot of feature extraction techniques or the dimensionality reduction techniques based on feature matrix decomposition. Okay, so I am going to explain that. Okay, so in day 7, I have shared one matrix decomposition technique. Okay, so in matrix decomposition, what is happening? Okay, see, matrix decomposition simplify matrix operations and linear algebra problems. So decomposition factor a matrix into simple component. Okay, matrix into simpler components. So there are a lot of decomposition techniques: LU decomposition, QR decomposition, SVD, support singular value decomposition, spectral decomposition kind of stuff. And this is one of the most simplest decomposition we are actually going to discuss. Okay, so let's say data set be represented as X element of R n cross D. Now നിങ്ങൾക്ക് ഇത് പറഞ്ഞാൽ മനസ്സിലാവുന്നുണ്ടാവും അല്ലെ? Are you getting this? Are you getting this?
Yes.
Yes, yes.
Yes, sir.
So X is a subset of, or X is an element of a space R raised to n by D, where n is the number of samples and D is the features. Okay, and what is the impact of a covariance matrix? What do you mean by a covariance matrix? Do you really know what is a covariance matrix? Suppose we have, and what is this variance? Can anyone tell me what is this variance? What is this variance?
Sigma square.
A sigma square is there, but what is that?
Deviation from mean.
Yes. If you have a set of observations, for that observation, we can actually find out a mean, right? Okay, we can find out a mean. Okay. And with the mean only, we cannot actually represent the behavior of data. See, suppose there is a class 1. Okay, there's a class 1. And for that class 1, for machine learning, they have scored marked like 48, 49, 50, 51, 52. Okay. And in class 2, the marks are 0, 1, 50, 99, 100. Okay. So from the observations itself, we can see that the behavior of two classes, C1 and C2, are entirely different, right? Is it clear?
Sir.
Yeah. Now, if you find the mean of class 1 and mean of class 2, what will happen? Mean of class 1 and mean of class
Both
2, what
is
will
nearly
happen?
50. Yeah, 50.
For the class 1, it's 50. For the class 2 also, it is 50, right? So with mean alone, can we represent the behavior of a class? Is it possible?
No.
No. Right? So how can I represent that? There we use the metric sigma. That is, what is that? What is that? Standard deviation. Or if you consider the square, it will be the variance, right? And how we can calculate that? It should be the square of sum of the squares of each observation minus mean, right?
Mean,
So this is 2 square plus 1 square plus 0 square plus 1 square plus 2 square. That value will be 2 plus 2, 4 plus 4, 10, right? Okay. And what about this? 50 square plus 49 square plus 0 square plus 49 square plus 50 square, right? What is the value there? 2500 plus. Can anyone tell me what is 49 square? 49 into 49. 50 minus 1 whole square. 50, 2500 minus
2401.
2401, yeah. 2401. 2500 plus 2401. So 4901. So this is the variance. Okay. So by observing this 10 and by observing this 4901, what one can conclude? 50 is the mean, right? Mu and sigma. 50 is the mean. And sigma is root 10. Maybe I can take root 10. It's sigma square, right? Root 10 will be, what is the root 10? Root 10. 3 point something. Such 3 point something.
Yes, 3 point. But I think we have some n also coming, n or n minus one, something kind of that also, right, sir? In formula.
Yes.
I don't remember exactly.
Yes, by divided by n. But that is a proportional value, right?
Yes.
Yeah. By n, but I can consider this as maybe 5000. What is the value? Root of 5000 will be some value.
Around 70 point something.
Yeah, 70 point something. Yeah. So by observing this 50 and 3.1 and 50 and 70 point something, one can easily understand, even though the average of these observations are 50, the other observations are very nearer to 50 if the variance is 3.1, right? And the other observations are far away from 50 if the variance is 70 point something, right? Are you getting it? the idea of variance?
ലാസ്റ്റ് പറഞ്ഞു ഒന്നുകൂടെ പറയൂ.
Yeah. From two observations, 50 and 3.1 something, and 50 and 70 point something, right? This is actually representing mu and sigma, right? So I have a collection of data D1 and I have another collection of data D2. So from this, what you can conclude? The mu of D1 is 50 and the mu of D2 is 50. So the average value, the mean value of both D1 and D2 are what? 50. Right? But to get this average, there will be a lot of other observations, right? We have to add all these observations, then we divide by n is actually giving 50, right? And the idea about other observations is that the other observations is very much nearer to the mean. That is why we are having a small variance. Small variance of 3.1. And here we have a big variance. That means the observations are not much nearer to mean. So if you think about the distribution of our data, if this is mean, the first data is actually having a distribution like this. And the second data is actually having a distribution like this. Are you getting it? So the observations are not too far in the first data, but far from the mean in the second data. Hope it is clear for you, right?
Okay.
Yeah.
Yes.
So then what is covariance? What do you mean by covariance? Covariance. If you have two set of variance is actually about one data, right? The variance is actually about one data, right? But the covariance is actually about two data. Okay, so if we have x1 and x2, 1, 2, 3, 4, 5 is the data, and 1, 2, 3, 4, 5 is the data, right? Then the covariance, okay, the covariance will be 1. Okay, the covariance will be 1 for this. Okay, because they are having a very similar behavior, right? And if you are having an entirely different behavior, the covariance will be different. Okay, the covariance will be having a big value, right? So this is the intuition, right? You have to keep in mind. So the covariance matrix is nothing but, see, if you have a data like this, x1, x2, x3, etc. up to xn, there should be a matrix, right? Then 1, 2, 3, etc. up to n, 1, 2, 2, 3, etc. up to n. So what is this? First row and first column, right? This is simply sigma square 1. Okay, that is simply the variance of first. But what is this? This is sigma 1, 2 square, or here sigma 2, 1 square. That is covariance of the second feature and the first feature. Covariance of the second feature and the first feature. So this is representing the ith row. Okay. And this is representing the jth column. What is this? This will be representing the covariance of the feature xi and covariance of feature xj. Is that clear? Is that clear?
ഒന്നുകൂടെ അത് പറഞ്ഞോ ഈ 1 2 പറഞ്ഞ 2 1 റോയും കോളും
ഇത് രണ്ടും സെയിം ആയിരിക്കും. The covariance of 1 with respect to x1 with respect to x2, the covariance of x2 with respect to x1 സെയിം തന്നെ ആയിരിക്കും. ഓക്കെ.
അനോട്ടേഷൻ അങ്ങനെയാണോ അറിയില്ലാത്തോണ്ടാട്ടോ സിഗ്മ 1 2 എന്നാണോ 2 1 എന്നാണോ എഴുതേണ്ടത്?
Both are same.
നമ്മൾ ഫെമിലിയർ ആയത് മറ്റേ രീതിയിലായതുകൊണ്ടേ
ആദ്യം റോ നമ്പർ പിന്നെ കോളം.
അതാ പ്രോബ്ലം.
അത് നമുക്ക് എങ്ങനെ വേണേ എഴുതാം. ബോത്ത് ആർ സെയിം ആക്ച്വലി. അല്ലെങ്കിൽ നമുക്ക് ഇങ്ങനെയാണ് യൂഷ്വലി എഴുതുക. കോവേരിയൻസ് ഓഫ് I, j. Okay. So the covariance, we compute the covariance matrix. Okay. So the covariance of a matrix is actually, or covariance of a data set is actually giving the idea about how much each feature is deviated from other feature. Is that clear? How much each feature is deviated from?
It's somewhat kind of correlation that you have.
Correlation and covariance are somehow different. They are related, but they are different. Okay. Maybe we can actually check on that. Correlation versus covariance. So covariance measure the direction of relationship, and correlation is actually giving a degree. Okay. Covariance is actually giving the direction, and correlation is actually giving the strength of the relationship. That is the difference.
Yes, sir. Okay.
Okay. So the covariance can be in between minus infinity to positive infinity, but correlation will be always in between -1 to 1.
1 and +1. Okay.
Yeah. So if the covariance is there, that is covariance of x and y is greater than 0, we can say that they are actually moving in the same direction. Okay. And how much that direction is giving a relationship, that is actually correlation.
If both are actually going in the same direction, one can actually reduce that feature.
Yeah,
right?
Yes. That is the idea we are actually going to tell here. So after getting this correlation, okay, this correlation is actually giving an idea of the directions of spread. How much variance are there between any two axes, right? That is, if there are two features, okay, so there are two features. Okay, we can actually draw an ellipse here. Okay, we can actually draw an ellipse here. Then that ellipse is actually representing that in x direction, the range of values are, or the variance is actually high. And here the variance is less, right? Then if you have three-dimensional data, it can be an ellipsoid kind of thing, right? So you can actually get the idea about variance of all directions. So ultimately, the covariance matrix is actually giving the idea of spread along each component. Is that clear? Is it clear?
Actually, if the spread is there, we can, that I understood how it is related to that covariance matrix.
Yeah.
Yes.
I will tell you.
I think maybe I'll think for some time later. It's fine. You please continue.
That thing need to be clear. Okay. So for that understanding, I have given a document here. See, this is a major problem everyone will face, because whenever people teach PCA, this concept is not clear. This will actually make confusions in everyone. So what I did was, see here. See. So here, this is an introduction to PCA, but that introduction itself will give the idea of this. Okay. Appearance of covariance matrix in variance expression. Okay. So this is all technical. And see, here we are actually telling a sample covariance matrix encodes all pairwise correlation between features. Okay. A sample covariance matrix encodes all pairwise correlation between features, since its elements sigma ij gives the covariance between I and j. So by solving the eigenvalue problem, okay, so by solving the eigenvalue problem, we find the directions in which the projected data is maximally spread out. So if you have the eigenvalues and eigenvectors of this covariance matrix, okay, eigenvalues and eigenvectors of this particular covariance matrix, it will actually give the direction of vectors where this maximum spread is there. See, if you simply visualize, if there is a three-dimensional data, okay, there is a three-dimensional data. That three-dimensional data can be projected into an XY plane, right? Into an XY plane, into a YZ plane, or into an XZ plane, right? Is it clear? Is it clear?
Yes. So,
yeah, for
actually,
everyone. Yeah, what I'm trying to tell you is, see, if you have a data in a three-dimensional space, I can show you like this. Suppose we have an ellipsoid like this, okay? And consider this is our data. Okay, spread of data. See, you can see that, right? Okay. So this is an ellipsoid, like an egg, right? Okay. And if you simply project this x, y, and z, okay, if you simply project this on x, y, and z, what will happen? What will happen? For a three-dimensional space, there may be an xy projection, right? And you can also project over here a plane like this. And you can project over here too, right? So sometime you may get an xy projection like this. Some xz projection like this. And yz projection like this. Right? So in xy direction, the variance is actually same, right? But here in the direction of z, we can see big variance, right? But the thing is, and likewise, we can actually do this if it is an ideal ellipsoid. But if the ellipsoid is like this, what is the direction of this particular data? If this is an xyz plane, can we say, is it parallel to x-axis? Is it parallel to y-axis? And is it parallel to z-axis? Can we say that?
No, maybe if you can say major axis of the.
Yeah, the direction will be like this, right? Somehow. Right? And how to get this direction? And what is this direction actually? These directions are actually the maximum. This is the direction which is having maximum variance, right? And maybe after that, some other axis like this, some other axis like this, and after that, some other axis like this, right? So, how to get this? These directions. To get this direction, if you have this data as a matrix of the form or the data m by n, the covariance of D, okay, the covariance of D will give you the directions of different spreads on each axis, right? The directions of each spread on each axis, right? And from that covariance, we need to find the axis which is having maximum variance, right? And to get that, and that should be what? Orthogonal to. And to get that, we can consider the eigenvalues and eigenvectors of this covariant matrix. Okay. Right?
One gives the magnitude, other gives the direction, right?
Yeah. So it will, the eigenvalues will give how much the spread is, and the eigenvectors will give the direction of maximum spread too. Okay. So
Norm x equal to norm y equal to 1.
Fancy Miss, you are not mute. Okay. So that is why we are actually considering this particular covariance. Then after this covariance, what we are actually doing is, the steps is actually different, simple. This is the only point we are getting confused. Okay. So keep in mind, if you have a data, then the covariance matrix will capture the spread across each pair of axes. And to get the maximum spread, the direction of maximum spread, in which direction we have to consider to get the maximum spread, the eigenvalues will help us. That is what we are calling as this gamma, that is the eigenvalues, and Q is the eigenvectors. So the covariance matrix can be represented. Okay, the covariance matrix can be represented as Q sigma Qt. That is the thing, Q sigma Qt. And if you see a numerical example like this, so eigenvectors indicates the direction along which the data varies the more, the principal directions, and eigenvalues quantify the amount of variance, amount of information present along each eigen direction. Okay. So eigenvector form a new coordinate system. Eigenvalues tell how stretched the data is along each axis. So how we need to do this? So this is the step we need to follow, the singular value decomposition. For that, what we usually do is, the steps you can actually follow. There is no need of mugging up these things. First, you have a matrix A, compute A transpose A, which is actually the covariance matrix. Then find the eigenvalues of A transpose A, get the singular values, that is the square root of eigenvalues. Then you have to construct the right singular vectors and the left singular vectors. Okay. By considering the vectors, then construct U and V and diagonal. Finally, you will get the decomposition. Okay. So I'm just illustrating this with a numerical example. You can actually go through this one more time. So A is 3113. A transpose A is equal to 10664. A transpose A is, the eigenvalues of A transpose A is 16 and 4. You are getting the singular values 4 and 2. Then you are finding out U, where 1 by sigma I into AVI, that A into each vector. Then decompose U, sigma and V transpose. Okay. And this is with a numerical example. Here we have how many features? 4 features are there. And how many observations? 5 observations are there. Now we have to reduce it into 5 observations and 2 features. That is our goal. So how you will do that? You have to first construct U. And how to calculate U? This is the step we need to follow for U. Okay. So you got U, you got sigma, that is the diagonal, this is the eigenvalues, singular values, this is the V. Now after getting the vectors, okay, after getting the U, V and sigma, what we have to do is, suppose you need to transform it into 2 features, right? So what are the top 2 eigenvalues? 12.3 and 5.2, right? 12.3 and 5.2. So this 12.3 and 5.2 need to be considered. These 2 vectors corresponding in U. Okay. So consider U2, first 2 columns of U. Okay. That is our first 2 columns in U. These 2 columns in U. Then we have to construct sigma 2, top left 2 by 2. Okay. Top left 2 by 2. That is this. Okay. Then first 2 columns of V. Then A into V2. will give you the reduced set of values. Okay, A into V2. See, this is actually the transformed two vectors. Okay. So the final reduced vector will be like this. The same procedure is actually explained in PCA2. Here also, we are doing the same thing. Okay. So PCA here, PCA will again do another kind of computation similar to this. Here also, the steps are, first, we have to consider this 1 by m into x transpose x. That is the covariance matrix we have to calculate. Then eigen decomposition, then select the principal components, then project the data. So first we have to take the x, and there is a step called centering. Okay, centering, then compute S, the covariance matrix, then do the eigen decomposition, select the k top k vectors, then project it. So for a two-dimensional data, we can actually see this. See, this is the entire data, and we can see the spread of this data is like this, and the corresponding second spread is actually in the this direction. Okay. So suppose you want to project this two-dimensional data into one, project all this data into this particular axis. Okay, project all this data into this particular axis. And how we can actually do this? Okay, consider this data sample. Okay, we have two different features, and these are the samples. Now we have to calculate the mean. Okay, we have to calculate the mean. Now subtract this mean from every data point, then the data will be centered. You can actually see the visualization, then you will understand how it works. Okay, you can actually do the centralization part, then find the covariance matrix. That covariance matrix actually represents an ellipse over here, and with that ellipse we can actually find the eigenvalues that and eigenvectors which represents the direction of maximum variance. Then select the column, select our data which is centered, and multiply it with V1. Then you will get the first principal, first projected value. Okay. So this is the illustration. That illustration can be explained with a code here. See, yeah. You will understand how it works now. So here I'm creating a random data, and the random data is actually plotted over here. Yeah, the random data is plotted over here. So this is our data. Okay, so there are around 100 samples. That 100 samples are distributed like this. Okay, now the second step. What is the second step we have discussed? We have to make it into center, and for make it into center, what we have to do? We have to calculate, or we have to calculate the mean vector and subtract every vector into from every vector, mean from every vector. So then it will shift to center. That is the second procedure we have done here. We are calculating the mean, okay, np dot mean of x, and we are subtracting x mean from every x. Then we will get the x center. So visualizing that, see, the data is actually centered over here, right? Okay, so the data at this point is actually now centered over here, right? And the next one is we have to calculate the covariance matrix, and the directions of the covariance matrix. See, the directions of the covariance matrix is red is the first direction. Okay. This violet is the second direction, and this brown is the third direction. So these three directions are orthogonal, and it will give the idea of in which direction the maximum spread is. So this is the maximum direction spread, then the second one and the third one. Okay. So after that, what we will do is you can actually see a covariance ellipsoid. Okay. So if the ellipsoid is actually having a major axis in the first components, see the first component, and the second major axis on the direction of this second eigenvector, and the third major axis on the direction of this third eigenvector. Okay. Now what we are doing is, suppose you need to get one-dimensional data to this axis. Okay. This is the first component axis, right? To this axis, you have to project all the data.
Sir, a confusion, sir.
Yeah.
Actually, here we can see three axes. Along with that, we can see some three vectors. Are they eigenvectors or?
They are the eigenvectors. The three axes are the same axes as that of x, y, z.
Okay.
Okay. So this ellipsoid is actually having the major axis in this direction. You're able to rotate, you can actually see that.
Okay.
Yeah. The second major axis will be like this, and the third axis will be like this. So this along this axis, the ellipse is actually having the maximum spread. That is, the data is actually having the maximum spread. Okay. Now, if you want to reduce this three-dimensional data into single dimension, what you have to do is consider the first axis, the first principal component only, project all data into that line. Right? Project all data into that line. Then from 0, you can get each point with a single value, right? That is the first principal component. Suppose if you want to reduce it into two values, now what you have to do is you have to consider a plane constituting the first principal component and the second principal component, and project all data into that particular plane. So in this view, we are not able to see that. To see this, I have just slightly changed the view like this. See? So an axis that connects the first principal component and the second principal component, consider a plane and project all data into that particular plane. Okay. So from this center, each data will be represented using two coordinates, right? So that is the first component and the second component. Likewise, for an n-dimensional data, you can project it into one axis, two axis, three axis, or it can be of n-1 axis. So this is the idea of what a principal component analysis. And don't worry about all this mathematical stuffs. Okay. To implement this is very simple. Just need to call, load the data. Okay. See, here you can see these are some correlation metrics and all. I can show you the last one. Okay. See, this is how we are actually going to do the principal component analysis here. So the thing is, just see, create an object of PCA, specify the number of components you need, n components equal to 2, do the calculation. That is what happening with this fit, and transform will project your data into that space. Then every data with 4 features now reduced into what? 2 features. If you do this with 3 features, you can actually get the 3 features. So the 4 dimensions are there for iris data. So either you can reduce into 3 or you can reduce into 2, right? I have never tried with 1. 1 is also possible, I think. 1 is also possible. Yeah, 1 is also possible. Okay. And one more thing is actually discussed here, which is called as linear discriminant analysis. Another kind of dimensionality reduction. There also, we can actually specify the number of components. Okay. Right? So the thing is, without losing the essence of the data, we can actually reduce the data into a smaller dimensional space. That is the advantage of what? Dimensionality reduction. And one advantage is we can do it for feature extraction. And see, suppose iris data is there. Usually iris data resides in 4 dimensions, right? Is it possible to display it, visualize it? No,
No,
right?
sir. 4
No.
dimension, no.
No. So to study about that relationships of each class of flowers, we can actually reduce that into 2 dimension and plot it in a 2 dimensional space. So without much losing the properties of the data, we can reduce that into a 2 dimensional space. Okay.
One doubt.
Yeah.
Always, as human, are able to visualize in 2 dimension.
For
Or
iris data.
maximum 3.
In 3, maximum 3.
So always the number of components will be 3 or 2.
It can be 3 or 2. If it's still the 3 is actually a projected figure, right? As we are plotting it on a 2D screen, the 3 is also a something like a projected to something on a 2D plane, right?
Yeah.
So better to project it on 2D, then we can get the actual essence. Otherwise, it should be something like an interactive space that we can actually, you have seen the GeoGebra, right? In GeoGebra, we can actually feel that 3D. GeoGebra, we can actually, sorry. Yeah. We can actually plot our things. See if you want. A pyramid like this. We can actually experience this. See, it's a very useful tool. Let's see, this is a point. See, we can see the point, a plane. So if you have a tool like this, 3D projections are good, but otherwise always do project on 2D. So everyone take time Please go through all the documents I have shared with you one more time. Okay. We are actually having a long break. So it will help you to get through the concepts. And I don't tell you need to mug up all the mathematics, but knowing the mathematics behind this will help you to visualize and understand and tweak the concepts for special use cases. But as a developer perspective or a project implementation perspective, particularly the students, there is no need of digging these maths. But as teachers, it's always better to understand this. Okay. And in the derivation of this, I'm not trying to do this derivation here because it will get more confusions for you. See, if you are interested, just go through this. Then you will understand why this particular thing, the covariance, is actually showing or appearing for finding out the spread. Okay. Yes. So anything else? And some of the techniques are actually given in that particular notebook, the wrapper method, the correlation metrics and all. Try to execute those things by yourself and understand the part. And almost the pre-processing techniques are over now. Now we will be discussing about some image processing and natural language processing techniques on the next class, so that we can actually understand how the features from images can be extracted, or features from text can be extracted, and utilize those things for the machine learning part. Okay. So try to watch the video one more time. Try to go through all the documents I have shared to you. Okay. So thank you. Thank you.